2005 Electronic National Electrical Code, or NEC, is copy and read protected, preventing direct installation onto a hard drive. A workaround involves using a CD Rom emulator. Specifically, Paragon CD Rom emulator version 3 can create a virtual CD on a hard drive. This allows the electronic version of the 2005 NEC to be read from the hard drive, circumventing the direct installation restriction. The Paragon CD Rom emulator version 3 is available for download. The cost is $29.95. Furthermore, the 2005 NEC search engine differs from those found in previous versions. This change affects how users navigate and locate specific information within the code. When using the National Electrical Code, it is important to understand the code structure. It is divided into chapters, articles, and sections. Chapters provide broad subject categories. Articles delve into more specific topics within those categories. Sections offer detailed requirements and specifications. Firstly, familiarize yourself with the chapter organization to quickly locate relevant areas. Secondly, use the table of contents and index to pinpoint specific articles and sections related to your task. Thirdly, pay close attention to definitions provided in Article 100. Accurate interpretation hinges on understanding the defined terms. Fourthly, review the scope of each article to ensure its applicability to your situation. Fifthly, consult the informational notes and annexes for additional guidance and explanations. Sixthly, use the search function in the electronic version to locate keywords and phrases relevant to your inquiry. Seventhly, cross-reference sections and articles to ensure a complete understanding of interconnected requirements. Eighthly, stay updated on any ROTA or supplements issued by the National Fire Protection Association, or NFPA, to address corrections or clarifications. Ninthly, consider attending training courses and seminars to enhance your understanding of the NEC and its application. Tenthly, seek clarification from qualified electrical inspectors or engineers when encountering ambiguous or complex code requirements. Furthermore, understanding overcurrent protection is crucial. Overcurrent protection devices, such as fuses and circuit breakers, are designed to protect electrical circuits and equipment from excessive current. The National Electrical Code, or NEC, specifies requirements for selecting and installing these devices to ensure safety and prevent fire hazards. Several key factors influence the selection and sizing of overcurrent protection. Firstly, the ampacity of the conductors being protected must be considered. The overcurrent protection device should be sized no higher than the conductor's ampacity unless specifically permitted by the NEC. Secondly, the type of load served by the circuit affects the selection. Different types of loads, such as motors, transformers, and lighting, have unique characteristics that require specific overcurrent protection strategies. Thirdly, the interrupting rating of the overcurrent protection device must be sufficient to handle the available fault current at the point of installation. Installing a device with an inadequate interrupting rating can lead to catastrophic failure during a fault. Fourthly, coordination between overcurrent protection devices in a system is essential to ensure selective tripping. Selective tripping minimizes the extent of an outage by isolating the faulted circuit while allowing upstream devices to remain closed. Fifthly, ambient temperature affects the performance of overcurrent protection devices. Diluting factors may be necessary in high-temperature environments to prevent nuisance tripping. Article 240.4 addresses the protection of conductors. It states that conductors shall be protected against overcurrent in accordance with their ampacities as specified in 310.15, subject to any permitted exceptions or modifications. Table 310.15b, 16 provides ampacity ratings for insulated conductors rated 0 through 2000 volts. These ratings are based on specific conditions such as conductor material, insulation type, and ambient temperature. Adjustments may be necessary for different conditions. Article 430 covers the protection of motors and motor circuits. Motor circuits require special consideration due to the inrush current that occurs when a motor starts. The NEC allows for the use of overcurrent protection devices with higher ratings than the conductor ampacity to accommodate this inrush current. However, specific requirements must be met to ensure adequate protection against sustained overloads and short circuits. Article 450 addresses the protection of transformers. Transformers can be damaged by overcurrent due to overheating or insulation breakdown. The NEC specifies requirements for transformer overcurrent protection based on the transformer's voltage, impedance, and winding configuration. Both primary and secondary overcurrent protection may be required. It's also important to understand grounding and bonding. Grounding and bonding are essential safety measures in electrical systems. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protection devices to trip and energize the circuit. Bonding connects conductive parts of the electrical system to create a low impedance path for fault current. The National Electrical Code, or NEC, contains specific requirements for grounding and bonding to minimize the risk of electric shock and fire hazards. Grounding and bonding serve distinct but complementary purposes. Grounding establishes a reference point for voltage and provides a path for fault current. Bonding ensures that all conductive parts of the electrical system are at the same electrical potential, reducing the likelihood of dangerous voltage differences. Several key components are involved in grounding and bonding systems. Firstly, the grounding electrode system consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes. These electrodes provide a connection to the earth. Secondly, the grounding electrode conductor connects the grounding electrode system to the equipment grounding busbar in the service equipment. This conductor carries fault current from the electrical system to the grounding electrode system. Thirdly, equipment grounding conductors provide a path for fault current from equipment enclosures and other conductive parts back to the service equipment. These conductors are typically wires or metallic conduits. Fourthly, bonding jumpers connect different parts of the electrical system together to ensure electrical continuity. Bonding jumpers are used to bond metal enclosures, metal raceways, and other conductive parts. Article 250 contains the NEC requirements for grounding and bonding. It covers various aspects of grounding and bonding, including grounding electrode systems, grounding electrode conductors, equipment grounding conductors, and bonding jumpers. Section 250.24 addresses grounding of service-supplied alternating current, or AC, systems. It requires that the neutral conductor be grounded at the service equipment. This grounding provides a reference point for voltage and helps to stabilize the system voltage. Section 250.118 lists acceptable types of equipment grounding conductors. These include wires, metallic conduits, and other approved means. The equipment grounding conductor must be sized appropriately to carry the available fault current. Section 250.104 addresses bonding of metal water piping systems. It requires that metal water piping systems be bonded to the electrical system to prevent them from becoming energized. This bonding reduces the risk of electric shock if a fault occurs. Section 250.130 addresses equipment grounding and equipment bonding jumpers. It requires that equipment grounding conductors and equipment bonding jumpers be connected in a manner that provides a low impedance path for fault current. Sizing grounding and bonding conductors is critical. The size of grounding and bonding conductors is determined by the size of the overcurrent protection device protecting the circuit. Table 250.122 provides minimum sizes for equipment grounding conductors based on the rating of the overcurrent protection device. Larger overcurrent protection devices require larger equipment grounding conductors. Bonding jumpers are sized based on the size of the largest ungrounded conductor in the circuit. Table 250.102c1 provides minimum sizes for bonding jumpers based on the size of the ungrounded conductors. In addition, you should also understand wiring methods. Wiring methods refer to the various ways electrical conductors are installed and protected within a building or structure. The National Electrical Code, or NEC, specifies requirements for different wiring methods to ensure safety and prevent electrical hazards. Proper selection and installation of wiring methods are essential for reliable and safe electrical systems. Several common wiring methods are used in electrical installations. Firstly, non-metallic sheath cable, commonly known as Romex, is a flexible cable consisting of two or more insulated conductors enclosed in a non-metallic jacket. It is commonly used for residential wiring. Secondly, electrical metallic tubing, or EMT, is a thin-walled steel conduit used to protect conductors. It is commonly used in commercial and industrial applications. Thirdly, rigid metal conduit, or RMC, is a thick-walled steel conduit used to protect conductors in harsh environments. It is commonly used in industrial and outdoor applications. Fourthly, liquidite flexible metal conduit, or LFMC, is a flexible metal conduit covered with a liquidite jacket. It is used in wet or corrosive environments. Fifthly, cable trays are open support systems used to support and route cables. They are commonly used in industrial and commercial applications. Article 300 contains general requirements for wiring methods. It covers various aspects of wiring methods, including installation, support, and protection of conductors. Section 300.11 addresses securing and supporting wiring. It requires that wiring be securely fastened in place and supported at appropriate intervals. This prevents the wiring from sagging or becoming damaged. Section 300.15 addresses boxes and fittings where conductors are spliced or terminated. It requires that boxes and fittings be installed in a manner that provides access to the conductors for inspection and maintenance. Section 300.4 addresses protection against physical damage. It requires that wiring be protected from physical damage, such as abrasion or impact. Different wiring methods have different ampacity ratings. The ampacity of a conductor is the maximum current it can carry safely without exceeding its temperature rating. The NEC provides ampacity tables for different conductor types and sizes. The ampacity of a conductor may be affected by factors such as ambient temperature, number of conductors in a raceway, and type of insulation. When selecting a wiring method, consider the following factors. Firstly, the environment in which the wiring will be installed. Wet, corrosive, or hazardous environments may require special wiring methods. Secondly, the type of occupancy. Residential, commercial, and industrial occupancies have different wiring requirements. Thirdly, the voltage and current of the circuit. High voltage or high current circuits may require special wiring methods. Fourthly, the cost of the wiring method. Different wiring methods have different costs, so it is important to consider the budget when selecting a wiring method. Additionally, understanding boxes and enclosures is also important. Boxes and enclosures are used to protect electrical connections and equipment. They provide a safe and secure environment for wiring terminations, splices, and devices. The National Electrical Code, or NEC, specifies requirements for boxes and enclosures to ensure electrical safety and prevent fire hazards. Several types of boxes and enclosures are used in electrical installations. Firstly, junction boxes are used to enclose wire splices. They provide a safe and accessible location for making electrical connections. Secondly, outlet boxes are used to mount receptacles, switches, and other devices. They are typically installed in walls or ceilings. Thirdly, pull boxes are used to facilitate the pulling of wires through conduit runs. They are typically larger than junction boxes and provide more space for wire manipulation. Fourthly, panel boards are enclosures that house overcurrent protection devices, such as circuit breakers or fuses. They distribute power to branch circuits. Fifthly, enclosures are used to protect electrical equipment from the environment. They can be made of metal or non-metallic materials and are available in various sizes and shapes. Article 314 contains the NEC requirements for boxes and enclosures. It covers various aspects of boxes and enclosures, including installation, support, and wiring space. Section 314.16 addresses box fill calculations. It requires that boxes be sized appropriately to accommodate the number and size of conductors, devices, and fittings installed in the box. This prevents overcrowding and ensures that the conductors are not subjected to excessive stress or heat. Section 314.17 addresses conductor entry. It requires that conductors enter boxes and enclosures through approved fittings that protect the conductors from abrasion. Section 314.27 addresses outlet box hood compatibility. It requires that outlet box hoods used in wet locations be compatible with the outlet box. Boxes and enclosures must be sized correctly. The size of a box or enclosure depends on the number and size of conductors, devices, and fittings installed in the box. The NEC provides tables and formulas for calculating the required box fill. Overfilling a box can lead to overheating, damage to conductors, and electrical hazards. In addition, it's helpful to know about raceways. Raceways are enclosed channels designed to hold and protect electrical wires and cables. They provide a physical barrier against damage, moisture, and other environmental factors. The National Electrical Code, or NEC, specifies requirements for various types of raceways to ensure safe and reliable electrical installations. Several types of raceways are commonly used in electrical systems. Firstly, electrical metallic tubing, or EMT, is a thin-walled steel conduit that is easy to bend and install. It is commonly used in commercial and industrial buildings for exposed or concealed wiring. Secondly, rigid metal conduit, or RMC, is a thick-walled steel conduit that provides excellent protection against physical damage and corrosion. It is often used in outdoor or harsh environments. Thirdly, intermediate metal conduit, or IMC, is a steel conduit that is lighter than RMC but stronger than EMT. It offers a balance of protection and ease of installation. Fourthly, flexible metal conduit, or FMC, is a flexible metal conduit that allows for movement and vibration. It is often used to connect equipment to a power source. Fifthly, liquid-type flexible metal conduit, or LFMC, is a flexible metal conduit with a waterproof jacket. It is used in wet or damp locations. Sixthly, non-metallic conduit, such as polyvinyl chloride or PVC conduit, is a lightweight and corrosion-resistant option. It is often used underground or in corrosive environments. Article 348 covers electrical metallic tubing, or ENT. Article 344 covers rigid metal conduit, or RMC. Article 358 covers intermediate metal conduit, or IMC. Article 350 covers flexible metal conduit, or FMC. Article 356 covers liquid-type flexible metal conduit, or LFMC. Article 352 covers non-metallic conduit, or PVC. The NEC specifies requirements for the installation, support, and grounding of raceways. Raceways must be securely fastened to walls, ceilings, or other structural elements. The spacing between supports depends on the type and size of the raceway. Raceways must be properly grounded to provide a path for fault current. The type of conductor also matters. The type of electrical conductor used within a wiring system significantly impacts its performance, safety, and suitability for specific applications. The National Electrical Code, or NEC, recognizes various types of conductors, each with distinct characteristics and limitations. Selecting the appropriate conductor type is crucial for ensuring a reliable and safe electrical installation. Several factors influence the selection of conductor type. Firstly, the ampacity of the conductor, which is the maximum current it can carry continuously without exceeding its temperature rating. Secondly, the voltage rating of the conductor, which must be equal to or greater than the circuit voltage. Thirdly, the temperature rating of the conductor, which indicates its ability to withstand heat. Fourthly, the environment in which the conductor will be installed, including temperature, moisture, and exposure to chemicals. Fifthly, the application, such as general wiring, motor circuits, or control circuits. Common types of conductors include firstly thermoplastic high-heat nylon, or THHN conductors, which are widely used for general wiring in dry locations. They have a high temperature rating of 90 degrees Celsius. Secondly, thermoplastic high-heat water-resistant nylon, or THWN conductors, which are similar to THHN conductors but are also suitable for wet locations. Thirdly, cross-linked polyethylene, or XHHW, conductors, which have excellent moisture and heat resistance. They are often used for underground service entrance cables. Fourthly, mineral insulated, metal sheet or MI cables, which consist of copper conductors insulated with mineral insulation and enclosed in a copper sheath. They are highly resistant to heat and fire and are used in critical applications. Fifthly, service entrance or C cables, which are used to connect the utility power supply to the building's electrical system. They are available in various types, including SEU and SCR. The NEC provides tables and guidelines for selecting the appropriate conductor size and type for different applications. These tables take into account factors such as ampacity, voltage drop, and temperature. Improper conductor selection can lead to overheating, voltage drop, and potentially hazardous conditions.